These are the 1.7 notes for pre-calculus, and it starts with an example, a real-world example, to get you the idea what an inverse function is. Remember that an inverse function is something that undoes another function. So typically we have examples like squares and square roots. If I square a number, if I have a function f of x that squares a number, the inverse function of squaring a number would be the square root. And the reason would be if I have an input on my original of 3 and I square the number 3, I'd get 9. And then if I take the number 9 and I plug it into my inverse function, which would be the square root of 9, I'd get an output of 3. And so my input would be 3 for the original and output 9. And then for my inverse, my input would be 9 and my output 3. So I end up back where I started. And that's the concept behind an inverse function. The example below is about raffle tickets, and it's to get the idea of real world. So the first example, you've got number of tickets that you would buy to support your band. This is a band fundraiser where they're selling raffle tickets for $2. And the first graph is showing if I buy a certain number of tickets, how much will I pay? And so I can go here, and the graph shows that if you purchase 6 tickets, the cost would be $12. Sometimes you want to look at a situation from another perspective, like I have a friend that's in band and I want to support them and I have $12. How many raffle tickets can I purchase? And using the graph, the inverse function, I can see that for $12 I can purchase 6 tickets. So just the concept and the perspective depending on what my input would be and my output. For the original I had number of tickets and cost, and then the inverse function cost and number of tickets. So you can, if you switch those, if you switch the x and y values, then you have an inverse function. One of the things we'll be focusing on is whether the inverse relation is a function itself. In this example it is, and it's because this is a linear function, and when I have the inverse it is also a linear function. So the question says, would the original be a function? The answer would be yes, because it is linear. And then is the inverse a function? And the answer would be yes, because it is linear. So example 1 is very exciting to look at whether something is an inverse or not. So let's focus down here on example 2. We have a parabola with the equation y equals x squared, and then we have the line y equals x, and we have the inverse relation. So the equation, the graph that's here in bold, this is our original, y equals x squared. It's a regular parabola that's been moved down 4 spaces. All inverses, to find the inverse relation, when you switch the x and y value, they are flipped over the line y equals x. So if I could bend my paper right around that line y equals x, the inverse and the original graph you can kind of see would match up, and you can try that on your own paper. So knowing that, the question that we're going to look at is, would the inverse be a function? And so if I'm going to draw 1, 2, 3, 4, 5, 6, 7, 8, right here when x is equal to 8, I'm going to draw a vertical line because we're familiar with the vertical line test, and we know the answer to the question is this sideways parabola, which is the inverse relation, is it a function? And the answer is no. Because it does not pass the vertical line test. But if we look at the original and we use the fact that it is a reflection over that line y equals x, this vertical line would be here on the original graph at y equals 8, because the line x equals 8, when I switch x and y, would be y equals 8. So there is a horizontal line test that would allow us to predict whether or not the inverse relation will be a function. And if it doesn't pass, if the original function does not pass the horizontal line test, then we know that the inverse relation will not pass the vertical line test. So down in the box below, the vertical line test indicates if a relation is a function. But the horizontal line test can be used to predict if the inverse relation will be a function. So if the original function passes the horizontal line test, you know that the inverse relation will pass the vertical line test and be a function. Here on our notes, right above the box, it says, if the inverse relation of f of x is also a function, then it's called an inverse function of f and is denoted with f raised to a negative 1. So if I use this notation, f raised to the negative 1 of x, it is stating that the inverse is also a function. A couple vocabulary words at the bottom. If a function passes the horizontal line test, it is said to be one-to-one. Or another vocabulary word is invertible. And both of those are used to describe a function who has an inverse relation that's always also a function. On the second page, how do we find the equation of the inverse function? And there's 3 steps. You want to rewrite the original equation by switching x and y, interchanging the variables. Second step, solve the new equation for y. And then the third step, graph the inverse and see if it passes the vertical line test. So here we have a rational function, y equals x minus 1 over x plus 2. We could do a little, we could graph the original function to see if it passes the horizontal line test to start. And so if we did that, we know that this is a rational function. The denominator cannot equal x cannot equal negative 2. So we know there's a vertical asymptote at negative 2. This rational function also has a horizontal asymptote at 1, which we will learn how to find that later in the school year. And if I plug in a value just to get an idea if it's going to be above or below in quadrant 1 or quadrant 4 here, if I just plug in, let's say, the point 3, 3 minus 1 is 2, 3 plus 2 is 5. At 3, this is equal to 0.4. Just by knowing that one point, I can get a pretty good sketch of the graph now. I know that this rational function would be down here in quadrant 4 and more quadrant 2. Has been translated a little bit, but I know basically. And x equals negative 2 was my vertical asymptote, and y equals 1 was the horizontal. So to find the equation of the inverse, I want to interchange my variables. So I want to put x is equal to y minus 1 over y plus 2. To isolate the y, first I want to get rid of the rational function, to get rid of the fraction. And to do that, I'm going to multiply both sides by y plus 2. And x, using the distributive property, x times y plus 2 times x is equal to y minus 1. If I want to isolate the y, I need to put all the variables with y on the same side. So let's subtract a y, and we're going to subtract this 2x. So I now have x times y minus y is equal to negative 2x minus 1. I still don't have the y isolated, but now I have two terms that both contain a y, and I can factor out that y. It's like dividing each term by y. So y divided by y would just be x minus y divided by y, which is 1. And then to isolate the y, I divide both sides by x minus 1. And my new function y is equal to negative 2x minus 1 over x minus 1. I can tell that this function then would have a vertical asymptote at 1, which makes sense because my last function had a horizontal asymptote at 1. So I'll draw the vertical asymptote. I also know that because this one had a vertical asymptote at x equals negative 2, my inverse relationship will have a horizontal asymptote at y equals negative 2. And flipping this function over the line y equals x in my head, I can see that this new function will be here. And it is also a rational function and will pass the vertical line test. Little hard to see. You might want to try graphing that on your calculator. Because it does pass the horizontal line test, I can use the notation. The inverse of f will equal negative 2x minus 1 over x minus 1. Example 4, I want to check and see if the inverse is going to be a function, and the original graph is the square root of x minus 1, which we know is a square root function that's been moved to the right one space. So if I start graphing that, it would go through the point 1, 0 instead of 0, 0 if I move it over to the one space. And I know the square root of 1 is 1, so over 1 up 1, and the square root of 4 is 2. So from my locator point, if I go over 4 and up 2, I can have a pretty good idea of the graph. I also know that this graph passes the horizontal line test, so that it will have an inverse relation that is a function. And one of the ways to graph that a different way than above is to switch your values, your x and y values. So I have in my original here, I have 1, 0 and 2, 1 and 5, 2. I can switch those points around to graph the inverse and graph the point 0, 1 and 1, 2 and 2, 5. So 0, 1, 1, 2 and 2, 5. I also know that square root and squares are inverses of each other, so that's going to have a shape of a parabola. So let's actually calculate the inverse for this one. I can see it as a function. Going through the same steps as above. X is equal to the square root of y minus 1. Square both sides. X squared equals y minus 1. So y is equal to x squared plus 1. And that is my inverse function. But it's not the whole entire graph of x squared plus 1. So I need to think about my domain. And we know that we're switching our x and y values, so we also know that our domain and range, domain is x and range is y, that when I switch x and y, my domain and range will switch. So if I talk about the original domain, looking at the graph, I can see that this graph has all x values that are greater than or equal to 1, so I can have a domain from 1 to infinity. And the range is all values, all positive y values, all my values of my square root function, all my y values are 0 to infinity. So that means the domain of my inverse will be the range of my original, or 0 to infinity will now be my new domain for my inverse, and 1 to infinity will be my range. So these will switch. Looking at the graph that I drew, domain is from 0 to infinity and the range is from 1 to infinity. That corresponds. So this inverse function, x squared plus 1, has a domain restriction from 0 to infinity. Two more examples. To prove that you really have an inverse, you want to prove that when you do a composite function, that it really does undo the original function. You end up back at x. For example, when I plugged 5 into the original function above, you have 5 minus 1, which is 4, and the square root of 4 is 2. And then if I plug 2 into the inverse, 2 squared is 4 plus 1 is 5. So they do undo each other. To show that algebraically, I wouldn't want to use a value like 2. I'd want to show it for every value of x. So here's an example of two inverse functions, both rational functions, 6 over x minus 4 and 6 divided by x plus 4. And I want to show that when I find the composite function of f of g of x, that they undo each other and I get x. So I want to take g of x, which is 6 divided by x plus 4, and plug that into the original function. So 6 over my input, which is 6 over x plus 4. And then I'm subtracting 4 because that's part of the function f. You can see that right away that the 4's would cancel, and you would have 6 divided by 6 over x. I'm going to switch notation just because sometimes we forget how to divide fractions, or that this is a fraction divided by a fraction. And we know when we divide fractions, 6 times x over 6, we multiply by the reciprocal. And the 6 is 6 multiplying by 6 and dividing by 6 will cancel, and you'll just get x. It should also be true that g of f of x is equal to x. So I'll take function g and substitute in f, which is 6 over x minus 4. And this function says take 6 and divide it by your input, which is 6 over x minus 4, and add 4. So I want to divide my fractions just like I did above. So 6 divided by 6 over x minus 4 is the same as 6 times x minus 4 over 6 plus 4. The 6's cancel and you get x minus 4 plus 4. Now the 4's will cancel and you'll get x. So both f of x, let me zoom out, or let me show you here, both f of x and f of g of x and g of f of x, both of those cancel, and you get 4. Not 4, you get x. Both f of x and f of g of x and g of f of x are both x, which show that they both undo each other and they're inverse functions of each other. Last example here, we have a word problem. Just to get the idea, if we set up a word problem with one input and one output, that we can look at the word problem from a different perspective and switch the input and output. So this is Kendra has a job where she's working and she's earning $8 an hour, and she always works 40 hours per week. After that, she receives overtime pay of 1.5, her regular rate for any time over 40 hours. Her total earnings is f of x, and for a week which she works x hours, so x is the number of hours that she works, or our input is hours, the function is f of x equals 320 plus 12 times x minus 40. The 320 is because she always works 40 hours at $8, and 40 times 8 is 320. The 12 comes from 1.5 times of 8. Half of 8 is 4, so 1.5 times 8 is 12. And that's the amount that she gets paid for anything that she works over 40. If we were truly going to write a function for this situation, this word problem, we would want to write a piecewise function and have a domain interval x is less than 40 for her first 40 hours, and then this would be the equation for the second 40 hours, or any additional hours over 40. Because of that, our domain is not everything. It's just the number of hours that work for this function that Kendra may work. So the domain, the lowest value it can be is 40. And the largest value is how many hours she could work in a week. And you really could put a number of things here. You could put 60 or 80. 80 hours in a week is a really hard, long work week. You could put maybe she's house sitting and it isn't a difficult job. She can actually sleep at the house. So I think 80 is extreme, but for this example, 40 to 80 hours I'm going to use because I don't know what kind of job Kendra has. If that's the domain, when I plug in 40, I can find the lowest amount her paycheck could be. Remember that X is in hours that she works, and Y is the amount that she gets paid. Let's call that her income. If I substitute 40 into this equation, 40 minus 40 is 0, times 12 is 0, so she would make $320. If I substitute in 80, now 80 minus 40 is 40. 40 times 12 is $480. 480 plus 320, I believe, is $800. Let me just check that over here on the side. 320 plus 480 is $800. So there's our domain and range for this situation. This is a linear function. Question number A says, explain why the inverse exists. Well, the inverse exists because it's linear, and we know that a linear function will pass the horizontal line test. In order to find the inverse, I switch my x and y and solve for y. There's a number of ways to do this. I would subtract 320 from both sides, and then divide both sides by 12. And then add 40 to both sides. So my function, my inverse relation, which I know is a function, would be x minus 320 divided by 12 plus 40. Now this function, sorry, it went off the page. This function, x minus 320 divided by 12 plus 40, has a domain of 320 to 800. Those are the possible values, possible incomes for Kendra if she works between 40 and 80 hours. And the outputs would be the number of hours she'd have to work for a particular amount. And those would be between 40 and 80. So that's what question B, part B is asking. What does F inverse and X represent in the inverse function? So in the original, X was hours and Y was income. Now, X is the income that Kendra can make, and Y, or if you want to call that F inverse, is her hours worked. The domain restrictions we have listed above for the original function. So for the inverse function, they're going to switch. So that would be, the domain would be from 320 to 800, and the range would be the 40. Her number of hours will be between 40 and 80. The last question asks us to calculate how many hours she'd have to work to earn $380, so we can substitute that into our inverse function. So the inverse of 380 would be 380 minus 320 divided by 12 plus 40. And 380 minus 320 is 60 divided by 12 is 5. 5 plus 40 is 45 hours. So if she had worked last week and earned 380, that means she worked 45 hours last week. And that's the end of the 1.7 notes.